So, hello friends. So today we'll see what is the concept of Fourier series, Fourier transform, FFT, DFT. You can say simply the first Fourier transform, or simply the what is the meaning of Fourier mainly. So we won't go in much details of mathematics because you won't understand the concept if you go in much depth of mathematics. So let us understand this by taking an example. Okay. So consider that you take some signal of some frequency, say for example some signal of say 10 hertz. Now as we are working in always in digital systems or digital signal processings, so you cannot take infinite number of samples of those signal. If you're drawing that signal on a paper, you can draw infinite number of points. If you simply draw a line, that will be infinite number of points. But if you're taking it in a MATLAB or any DSP processors, you cannot take infinite number of samples. You have to take finite number of samples. So simply we need to divide the time axis in some finite number of points. So consider if this is the time axis. Uh, don't consider this as a bin. Consider this as the time axis. So you are dividing this time axis into say n number of points. So here if you consider the 8 points of the signal, so that will be time axis will be divided into the 8 parts. So like that. So we are picking the samples after some specific interval of time so that you get finite number of samples of this entire sine wave. If you are having the sine wave like this, we'll pick some finite number of points. So each point is based on the interval of ts, the sampling time ts, or 1 by fs, the sampling frequency if it is 1 by fs. Now if you're considering like that, your fs is 1000 hertz. If you take the 8 point FFT of such signal, consider if you're taking the 8 point FFT of such signal means what? You are dividing the frequency region into 8 parts. You have the frequency region of 1000 hertz, which is a sampling frequency. You are dividing that into 8 equal regions, 8 equal parts. So one part is 125 hertz. This is called as FFT resolution. Where sampling frequency is 1000 hertz, we are taking the 8 point FFT or 8 point DFT. You are having the one part as 125 hertz. So if you are giving a DC signal which is having the zero frequency, so or we can rather just before that we can see this this is the entire region of say 1000 hertz. You are dividing into the 8 parts. If it is divided into the 8 parts, each part is of 125 hertz. Okay, starting from 0 hertz. So this is called as bin number 0, or you can say bin number 1, whatever as per your convenience. So if you are applying a DC signal to the FFT, the DC signal has zero frequency. Say if you are applying a 1 volt DC signal, which will look something like this in time domain. 1 volt DC signal, if this is applied to the FFT, your FFT will simply show one peak here. Or out of these 8 values, you are having these 8 values, this first value will be having the value of 1. Why 1? Because your DC signal is amplitude of 1 volt. Now, if you are applying suppose sine or cosine signal of 125 hertz, you will be getting one peak here, another peak here, because your sine or cosine signal contains positive as well as negative frequencies. Now, main thing is if your cosine or sine signal has peak amplitude of 1 volt, here you are getting two peaks of zero point 0.5 volts just to satisfy the law of conservation of energy. Similarly, if you are getting the or inputting the signal of 250 hertz, then you'll be getting one peak here of zero point 0.5 volts, another peak here of zero point 0.5 volts. Total it is 1 volts. Again, if you're having 375 hertz, you'll be getting one peak here, another peak here. If you are applying a 500 hertz signal, then you do not have any other bin which can represent 500 hertz. So you'll be getting a peak here. The complete peak amplitude is 1 volt because you are applying a 1 volt cosine or 1 volt sine signal, but you do not have any other thing like plus 500 hertz. So you'll be getting a peak here itself. Now, this is the concept of FFT. So you are getting the 8 values after 8 point FFT. What this first value means, it is the DC content in the signal or the signal which is having the 0 hertz. This tells 1 plus 125 hertz, another tells minus 125 hertz, this tells 250 hertz, this tells minus 250 hertz, and so on. Now, What will happen if you are applying a signal which is having the frequency higher than 500 Hertz? So as you know, your sampling is 1000 Hertz. You are applying the signal which is more than 500 Hertz. Means you are not satisfying the sampling theorem or the Nyquist theorem. Means your signal will get aliased. Aliased means what? You will be getting the signal frequency value which is out of all these values, because you do not have any other value available here. Your FFT or your system will treat that signal having having the frequency out of any of these values, or we will see this in MATLAB in much details. Okay, so let us see this simple code written for that. Just as a syntax, as I told you, the Fs is 1000 sampling frequency. We're taking the 8-point FFT of the signal. Then we have plot the signal. This is the cosine signal we are plotting. Then we are taking the FFT of the signal. So simply, if I am using the for loop is, we will gradually generate a signal. Now, for example, first we'll generate a 0 Hertz signal. Now let us see what happens. Now signal is a 0 Hertz signal, as I told you. So as I told you in the chart, this pin is showing you the high content because your DC signal is of 1 volt. So you're getting the amplitude of 1 volt. Signal is a DC, means your frequency is 0. So you're getting the first bin as the higher. So what is this second figure is simply, as I told you, if you see this part, here are the negative frequencies, here are the positive frequencies. But for human convenience, this negative frequency should be on the left hand side. But FFT calculates this as just shown here. So we want to move these negative frequencies just on left side just for visualization purpose. So MATLAB does this for us if you're using the function called FFT shift. If you just say FFT shift, it will move these values on the left side so that it will be properly visible and understood. So this, you can see this pin is higher, means you have DC signal of amplitude of 1 volt, and means you are getting the peak at 0 hertz, which is of value 1. So similarly, if you are taking the next frequencies, you can see this. The frequency is 125 hertz. You are getting the peak in this second bin and eighth bin. You can look at this chart, this bin and this bin. So you're getting the peaks in these two bins of each of amplitude of zero point 0.5, because your cosine is a peak amplitude of 1 volt. So just to satisfy the law of conservation of energy in time domain as well as in frequency domain, you can just say these if two are added, totally you'll be getting the 1 volt. So same as time domain. This is for 125 hertz. So similarly, it will be for 250 hertz. You're getting the peak in this bin, third and seventh bin. You can say this bin, 250 hertz here and here. Next is the fourth bin, which is 375 hertz. And now like this, if you go, now it is 500 hertz. Now, as I told you, there is no positive frequency side available in your bin, which can represent positive 500 hertz. So there is only one bin. You will be getting complete 1 volt in single bin, which is a fifth here, the fifth bin, which is the minus 500 hertz if you see in a frequency axis. These two figures are same, just as I told you, the negative frequencies are more on this side, just for our visualization purpose. And this is called bin number. Here we are just naming, after rearranging this negative frequencies, we are just naming this as the frequency values. Now this is all for your up to 500 hertz. Now see after this how the aliasing occurs. Now your signal frequency is 625 hertz, but your sampling is 1000 hertz. So you are sampling below Nyquist rate. Means your signal is 625 hertz, but you are sampling at 1000 hertz, which is not satisfying the Nyquist criteria. The FFT system or DSP system will treat this 625 hertz as some other signal, which is having the peak in this fourth and sixth bin, means 375 hertz signal. If you're considering peak here, means this is a 375 hertz signal. You remember your signal is actually 625. You're sampling below Nyquist frequency. That signal is treated as 375 hertz signal. Similarly, if you go again, you can see if your signal frequency is 750 hertz, but you're sampling still again below Nyquist rate, that will be treated as 250 hertz signal. When the signal actually is 750 hertz signal, that will be treated as 250 hertz signal. So getting the peaks in third and seventh bin, that is, if you see the frequency axis for better visualization purpose, it is 250 hertz and plus and minus 250 hertz. So signal is 750 but treated as 250 hertz. So similarly, we'll see further. Now your signal is actually 1000 hertz signal. You are sampling again with 1000. You are not at all satisfying the Nyquist criteria. Therefore, your signal peak lies within the first bin. And if you remember, the first bin is always treated as the zeroth bin, the 0 hertz bin. Sorry, 0 hertz bin means the bin that represents the DC content. So it says, or FFT says, you have DC content in a signal because FFT is not able to recognize the 1000 hertz signal that is treated as DC signal. 1000 minus 1000 becomes 0, or if you in a frequency axis, if you see, you will see the peak at 0 hertz. The signal which is having the frequency of 1000 is treated as 0 hertz signal or DC signal. It is actually 1000 hertz cosine signal. It is treated as a DC, which is a constant amplitude signal, something like this, which 1 volt. So this is actually the aliasing. The amplitude is okay. Amplitude level is 1 volt, which is correct, but frequency value is totally different. So what we can say is if you're sampling with same signal frequency or same frequency as signal frequency, if your signal frequency is 1000 hertz, sampling frequency is also 1000 hertz, signal is treated as 0 hertz signal, the DC signal. Therefore, you must satisfy the Nyquist criteria or you should sample more than the Nyquist frequency. So this is all about the aliasing, FFT, the concept of FFT. So just simply finally we'll see how the spectrums look like if you just run in one go. So first it is 0 hertz, then the frequency is 125 hertz, then 250 hertz, 375 hertz, this is 500 hertz, which is treated as minus 500 hertz, then aliasing 375, 250, 875 hertz signal is treated as 125, and now finally the 1000 hertz signal is treated as the 0 hertz signal or DC signal. So this is the concept of FFT, the concept of frequency bins, the aliasing, or how the aliasing occurs, what happens after aliasing. Generally, when we are studying the subject, we know aliasing, but we never consider about what happens after aliasing. After aliasing also, the frequencies are reconstructed, but those frequencies are something else or other than what we are actually inputting to the system. So that is called as aliasing. The aliasing is this meaning of this word, if you search, it is called as something else or interpreted as something else. Okay, thank you.